It is a pleasure to introduce our last speaker, Cheng-Xing Wang, from the University of Pittsburgh. The title of his talk is Geometry and Two-Sided Asymptotics in Constraint Quantization.
Yeah, thank you, Marino, for introducing me. My name is Chen-Xing Qian, and I'm from the University of Pittsburgh. So today I'm going to speak about the geometry behind the constraint quantization and a two-sided asymptotics formula that I developed from it. And the talk has two parts, though. The first is about the setup and upper asymptotics from the projection geometry. And so secondly, I will explain a geometric condition under which a lower bound at the estimate can also be built up. So let's start from the classical setting of the quantization problem. So quantization in sense of graph analogy is the problem of approximating a probability measure by a finitely supported discrete measure. So concretely, we are looking for a finite set with at most n points, which is called the quantizers, or to be called codebook in the applied sense. And so the quantizers minimize the functional in LR distance here. And so the infimum of the functional raised to the 1 over r power is called the nth quantization error, so denoted here ENR. And when r tends to infinity, the problem becomes a supremum over the support of P, and the quantity becomes the covering radius, and it's only related to the support of P. So this problem can be interpreted also in the sense of minimizing the Wasserstein's distance in the sense of the optimal transport. And so in a recent paper by Tandy and Rachel Tari, yes, they propose a natural variant of this question. So if the quantizers are confined in a closed set, so what properties do we have in this problem? And this problem is called the constraint quantization problem. And we can define the functional ENR and EN infinity in a similar sense. The only difference is the quantizers are confined in a closed set S, right? And so in their 2026 paper, they have verified the case that if the moment of the probability P is finite in R, then the functional is well defined. And here a little bit difference is because the constraint closed set may has a positive distance from the support of P. So we have to subtract E infinity R. So this means that E and R, when n comes to infinity, is no longer zero anymore. So we need to subtract another quantity, E infinity R, and we denote the new error quantity to be E tilde n R in this case. And next, the thing is the dimension problem of quantization. So the aim of the quantization dimension is to study the rate of decay of the errors. And they are, so precisely they are called the lim sup and the lim are called the upper and lower quantization dimension in this case. And so, and we can, in a similar way to define the constraint quantization dimension in the terms of the quantity, the error quantity E tilde n R, as I just introduced in the previous slides. And what's the good thing about the quantization dimension and why it's called a dimension is because typically for a set good enough, so the decay rate of the arrow has the rate of e power negative 1 over d. And the quantization dimension in this case just coincide with other dimensions like Hausdorff dimension, Minkowski dimension, and the regular dimension. And precisely so Krockner studied 10 years ago uh, about the property of the quantization dimension on a stable Riemannian manifold. And if a probability is ADR, then the upper and lower quantization dimension in an unconstrained case is equal to the dimension of the manifold itself. So, so in the 2026 paper, Pandy and Rachel Tari, they studied a lot of cases of the constrained quantization problem, and they concluded that the behavior of the constrained case is very much different than the unconstrained case. And so why it's hard and what's the difficulty here? It's because the constraint case, it relies on two ingredients. So one is the constraint set S, and another is the support of P. So the positioning of S and K with respect to each other and the geometry of themselves really matters. So in this project, so a technical object I introduced to study the upper asymptotics is called so pi s here is called the metric projection. So we are projecting from one point to the closest point in the constraint with the smaller distance, and the projection is not usually single valued. It's usually multi-valued. And so the central object we're studying here is pi sk here as a union of the projection of each point of the support k. So to study more precisely, we need to use the Kuratowski real and Zewolski measurable selection theorem, which means we can select a measurable selector from the multi-value projection map. And so the object we are studying is the push forward measure of the probability measure on the projection pi sk. Now, so we also the object pi sk usually have some good geometric property in the next slide. So if the geometric object is regular enough, then the pi sk is sometimes single valued in a tubular neighborhood of S. So the cleanest case in this case is a positive reach set. So reach is a quantity defined in a tubular set of S. And if the reach is positive, then the projection pi s is single valued locally. And so what's better is it's also locally Lipschitz here. And the case includes the compact C11 submanifold by the Federal theorem. And a more flexible case here is the Prox regular sets. So local Prox regularity means so near the set, every nearby point has a unique projection onto S. And equivalently, it satisfies a uniform exterior bulk condition along the proximal normal direction. And another important case is a convex set. Yes, it's Hilbert space 101, right? So a convex closed set has a single value projection, and the projection is also one Lipschitz. So to emphasize this in the general framework of the upper asymptotics and the lower asymptotics, we don't assume any of this specific condition. We only assume some set theoretic conditions the and some ADR conditions in the similar way. Um, so the next page is the main theorem about the upper asymptotics. So we impose a geometric condition U here. So which means there exists a infinity sequence of quantizers which approximates the projection pi sk in the Hausdorff distance. And then we have so and then we have an upper bound as so here. And from this quantity, this this implies that the quantization dimension when r is equal to infinity and when r is not equal to infinity is bounded above by the Hausdorff dimension the the of the projection set. And we can use some so in a very traditional way, if we have the results on the Hausdorff dimension, and we can extend this result to the box dimension here. So the quantization dimension is also bounded above by the box dimension of the measure, and also with respect to the projection here. So mu here is the push forward measure of the probability. So the quantity here is the central gradient in the upper asymptotics because um, so so basically we are pulling back the unconstrained quantization error to the case when to a case of to the case of unconstrained quantization on a compact set. So let's look at the next slide here. So the strategy here is the constrained quantization problem can be pulled back on an so as an unconstrained covering problem on a compact set if we suppose the hypothesis U here is correct. So the step one is we can prove a lemma which implies an upper bound. So remember the left-hand side of the inequality is just the E tilde. It is just the E tilde, an infinity, and it has an upper bound of an infinity covering radius of pi sk itself. So the next step here is we can, because pi sk is compact, and in this case, all the quantizers are also in the set pi sk. So we can do a compact covering. Uh, so we can do a compact covering, and by a stopping time argument, we can show that so the product n times e of n infinity. Uh, uh, Here d is a typo. It's just n times n infinity. It's less or equal than a constant which is only dependent to the dimension itself. It's uniform on n. And then the third step is we can transfer the upper estimate by push forward the bound to the measure t push forward p on the on the on the projection pi sk, and by the monotonicity of the quantization error with respect to r, and then we can show the the result, and by the definition we have an upper bound with respect to the Hausdorff dimension, and we can extend it to the box dimension. Yes. So the narrative when we are doing the upper bound is to reduce the case to a smarter set pi sk, which is compact, and we can do that by a compact covering principle. And the lower bound is more subtle. So the starting point, let's introduce a new identity, E delta Ni, which is an integral of, so with respect to each Vi of a new function h here. So h is a function here, which describes the price you have to pay if you are approximating with the quantizer element ai instead of the nearest projection point tx. So I also have another function GAI here as the distance of the quantizer to the nearest projection point. And so the aim decomposing the two functions is, so in good cells, in good Voronoi cells, H is coercive with respect to the quantity G, which means H has a should have a lower bound with respect to G in some good set. But actually, in some bad cells, the coercivity condition fails. So here we define the concept of a good set here. So fixing the threshold parameter lambda and a scale parameter t, we define a good set as a set where the function hi is coercive again with respect to t, lambda, and g. So why I'm doing this? Because this harmonic analysis technique, they naturally introduce a new research quantity here. So eta n lambda t. So which is the sum of all the masses of the Voronoi cells intersecting with the good set. So this is a total good mass portion. And actually, the so whether the so whether there are lower asymptotics, it relies on whether the quantity eta n stays bounded below as n comes to infinity. So this is a crucial quantity here. So the lower bound theorem says the following. So more precisely, under the hypothesis L, so the hypothesis L is a short notation saying that the quantity eta n remains bounded below. And we also suppose the push forward measure is upper or false regular. Then the lower constrained quantization dimension are bounded below by the Hausdorff dimension of the push forward measure. And also, a surprise is if we are combining together the upper condition U, and we suppose T is surjective, and more precisely the push forward measure is DADR, then we have a strict equality here. So everything here collapses to one number. And so one remark here is, if there exists a sequence of quantizers which lies in the constraint rather than the projection, then L is automatically true. But if it's not true, so under some variant condition L1, we can allow a perturbation argument. We can construct a quasi quantizer, which is not actual quantizer, but it preserves the properties with some acceptable errors. Then we can also recover the condition L. So let me introduce the interesting example here. So this is an example uh, discussed in the work by Rosenblatt and Rachel Harvey several years ago. And if P is uniform, so in this case, the constraint set is the unit disk, and the and the and the compact of the probability is the unit circle. So they have calculated that the optimal quantizers in this case it's the vertices of a regular n-gon, the the radius here is denoted by rho n, which is strictly less than one, but approximating the boundary of the unit circle. So the the condition L, the condition of the lower bound automatically holds. And in this case, we can conclude that uh, the so the upper and the lower quantization dimension here, they coincide with the regular dimension one the of the of the dimension of the unit circle here. And this is the textbook case where everything exactly works. But so in the next pages, I'm also going to show you a case when the geometry is going to work against us. So here is a counterexample. If so, let S to be the unit segment in the x-axis, and let gamma h to be a parallel element with a fixed height h, a positive fixed height h, and let P to be the uniform distribution on gamma h. Then we can, so the projection in this case is just the S itself, and the dimension here is one. And let's focus now on the calculation of the function g and h here, and we can notice that h has an upper bound as g squared over 2h here. So this is so the function h is quadratic in terms of the horizontal displacement of g. So and in this case we can notice that because the one-dimensional quantizer in this case is an equal length partition of S here. And so the quantizers are placed in the scale of 1 over n. But here we notice that the function HA has a has a has a quadratic scale, and the quadratic scale may overcome the linear scale of the quantizers. And let's be more precise. So we have already calculated that HAI has an upper bound in this case of 1 over n squared. And and uh, and if we want to make h is larger or equal than lambda t plus g, then we can find that if we select a scale Tn as tau over n, then for sufficiently large n, the quantity is equal to 0. So this says that the lower asymptotics doesn't hold as 1. And precisely, we can calculate that the quantization dimension in this case is 1/2. So it's no longer equal to 1 anymore. So this is a counterexample because, so from this example, we can see that, so the constraint is no longer contacting the the support of the probability measure. And actually, there is an unpublished result here. And so the natural question here is, when does the quantity eta n stay bounded below? And this result is the centerpiece of this talk. And here I consider a flat model, which means it's codimension one. It can be a codimension one affine space of an Euclidean space. And so I prove that the quantity is state it has a lower bound as the quantity of CB and CF. So first so we denote the base analysis condition here. It's the summation of the probability uh, of uh, of an annulus intersecting with the inverse image of the Voronoi cell. So which means mu has to have enough mass at a moderate radius around each quantizer element. And the second one is the fiber contact condition here. So it's an analog of the lower Cardassian packing condition. So the here the probability that T and Tx has some closer distance within a kappa cone is bounded below by the measure of a measurable set E. So let's look at more precisely the two quantities here. It's so they are basically the infimum of the base annulus quantity and the infimum of the probability over the push forward measure. So this is called a base annulus quantity, and this is called a fiber contact quantity. And we can show that the lower bound is related to these two quantity, and these two quantity is geometric meaningful. It's more incredible than the quantity eta n here. So it's a clean factorization, and these two quantity they imply so the base annulus quantity so describes the inside geometry of S, and the fiber contact quantity it describes the geometry across S and K and how they intersect with each other. And so I think I need to move on the last page. Yeah, it's a natural analog of the Cardassian packing condition in harmonic analysis. So recall that the usual Cardassian condition is the volume measure of a tint over a sphere is bounded above by the surface measure on a set. So here we can also notice that the terms inside of T, it's so it is saying that Tx is bounded within a kappa cone of X here, and it's bounded below. And so it's bounded below, and it has a lower packing in normal kappa cones over S. So and also here, this holds as well in arbitrary scale of the function S. So let me recap what's going on for the lower dimension. So we are studying the quantity eta n, and we decompose. So we studied the lower bound of the eta n, and we decomposed one of the lower bound of eta n as two quantities, two geometric quantities. One is base annulus and another is fiber contact. And fiber contact quantity has a dual structure as a Cardassian packing condition. So I think this is the direction in which we can work on in the following work. And thank you. This is the end of my talk. And
Thank you.
Yeah.
Yeah. Thank you for the nice presentation.
Yeah. Thank you.
Okay, let me stop the recording then.